Okay, so we had this particular graph in a problem from, I think, the in-class materials. So here we are asking at which points this function is continuous. And so we can see just by looking at it that there's going to be issues here. This looks like a jump discontinuity. Here at -8, there's a removable discontinuity. And then here at -2, the function is approaching something, well, it's approaching infinity from the right side, and it's approaching 3 from the left side, so there the limit does not exist. So each of those is going to be a point of discontinuity. So G is not continuous at x equals -2 and 6, and these are both for the same reason, and that is that because the limits do not exist there. So those two are points of discontinuity, and at x equals -8, the limit does exist there. It would be approaching -6, but the value of the function is not equal to the limit because f of -8 does not equal the limit as x goes to -8 of, oh, sorry, I'm using f and this should be g of x, because the limit does not equal the value of the function there. Okay, so that means that g is continuous everywhere else on this interval. So we're assuming that the function's only defined from -12 to 12, so starting from -12, the function is continuous up to, but not including, -8, right? And then from -8 up to, but not including, -2. And then from 2, okay, from, sorry, -2 up to 6. And then finally from 6 to 12, right? So, yeah, you could write it this way. I also wouldn't mind if instead of using this is a union symbol, you can just use a comma between the intervals. That's fine too. Okay, so if we have two continuous points, we can two continuous points. That doesn't make sense. So if we have two functions that are continuous at a point, we can combine them and get more continuous functions. So if f and g are continuous at a, then so are f plus g, f minus g, a constant times f, f times g, and so long as g of a does not equal 0, also f over g, right? Okay. So these are not too hard to prove. They basically come from the limit laws. So the fact that we can use the limit laws for each of these sort of gives us directly the continuity there. So I'm not going to go over those, but yeah, that's how you would do that. So a useful fact is that if a function f is continuous at x equals b, and the limit as x goes to a of a function g of x is equal to b, then the limit as x goes to a of f composed with g is equal to f of the limit as x goes to a of g of x. Okay, so this means that we can pull the limit inside of f, right? And take the limit of g and then evaluate f at that limit. Okay, so this is a lot more natural if you do just an example. So here we have the limit as x goes to 0 of e to the sine of x. Now, e to the x is a continuous function. It looks like this, right? An exponential function. It's continuous on the whole real line, so we really don't need to worry about points of discontinuity. And so here what we're going to do is our g of x, so our f of x, our outside function, is going to be e to the x, and then our g of x is going to be sine of x. And so notice that f composed with g would be e to the sine of x, right? Which is the thing we're trying to take the limit of. Okay, now this is going to be equal to the limit of, so how do I want to write this? I think it will be less confusing if I just write it directly. So this is equal to e to the limit as x goes to 0 of sine of x. Okay, so the idea is I'm taking this limit, which is on the outside of this continuous function, and I'm putting it inside to where the variable is. And that variable is itself a function, so I just go ahead and take that limit. As x goes to 0, sine of x goes to 0. So we just get e to the 0, and anything to the exponent 0 is equal to 1. Okay, so that is our answer here. This is actually a nice thing to have. But you have to be careful that when you do this, you have a continuous function, right? It's very important that you have that f is continuous at x equals b. If you don't have that, then you don't necessarily get this, and so you have to be careful. Okay, now we have one more thing to cover in this section, and that is the intermediate value theorem, right? So let's go ahead and write down what it is, okay? So suppose f is continuous on an interval a, b, and f of a is not equal to f of b. Okay, so it's just not equal at the endpoints, right? If n is any number between f of a and f of b. Okay, so let's go ahead and start drawing a picture. What we have is an interval a to b. F is continuous, and whatever the values of f of a and f of b are, they just are not equal to each other. So let me draw this a little. So say it looks like something like this, right? Okay, so say my function looks like that on this interval. Here is f of a, here is f of b, right? Now, I am assuming that f of a is less than f of b. That's not necessarily the case, so I'll probably just draw a corresponding picture for the other case. But so now we're assuming that we have a number n that falls between f of a and f of b. So this is on the y-axis, right? Okay, so what the intermediate value theorem says is that if this is true, then there exists a number C in the interval a to b, so somewhere in this interval down here, such that f of c is equal to n. That's right. Okay. Now, this sounds strange, but it's actually pretty intuitive if you just look at the picture. So here's my, I'm just going to draw a line through here. So you can see that if f is continuous and it has to go from f of a and somehow make it to f of b, it has to pass through this green dotted line. No matter how I drew f, no matter how crazy it looked, because it is continuous, at some point it's going to have to pass this line, right? And so that is basically what the intermediate value theorem is saying, right? So the line y equals n will have to intersect the graph of f. So each of these conditions is important. So that f is continuous, f of a does not equal f of b, right? So those two conditions are both important. Notice that if I did have, so let's block this off like this. Okay. If f was discontinuous, then I don't necessarily get this, because I could have a situation where here's f of a and here's f of b, but okay, and here's a and here's b. So I have my values of my function like this, and I'll draw my line. This is y equals n. Okay, now what could happen if f is discontinuous is we could have a jump. So it could pop from down here to up here, right? Without ever passing through the green line. So that is right, an example of why this is important, that f is actually a continuous function. Okay, so let's do an example of applying this. So this says we're given this polynomial, so it's 4x cubed minus 6x squared plus 3x minus 2, and we want to show it has a root between 1 and 2. So if you don't remember, x, or let's say p, the function, has a root at x, or let's write x equals a. How about that? P has a root at x equals a if p of a is equal to 0. So this means that the function passes through the line y equals 0, right? So if we want to so say our function looks like this, then each of these points where it passes through the x-axis, these are all roots. Okay, so that's what we're looking for. And we want to show that it has a root between 1 and 2. And so we can use the intermediate value theorem, and all we have to do is show that, so this is a cubic function. It's continuous because all polynomials are continuous. So first of all, let's write that down. P of x is continuous because it's a polynomial. And just so this, I mean, I'm being a little bit lazy by, because all polynomials are continuous. But if you think about it, I'm going to erase this in a second. So it's pretty clear that y equals x is continuous. And then if we use our these facts, right? We can create any polynomial just from y equals x and a constant. We can create, something that looks like this, right? And then we know that since each of those pieces are going to be continuous, the whole thing is continuous. So it's not too hard to prove that all polynomials are continuous. Okay, so we have a continuous function, and we just want to show that basically we have on one side of the interval the function is negative, and on the other side of the interval the function is positive. So all we need to do is just check that that's the case. So plug in 1, we get 4 minus 6 plus 3 minus 2. So that is 1. Wait, is it minus 1? Yeah, it's minus 1. Okay, and then we plug in 2. So we get 4, 2 cubed minus 6 times 2 squared plus 3 times 2 minus 2. So in the first, this first one is going to be 2 to the 5th, which is 32 minus 24 plus 6 minus 2. Okay, so if you do this in your head, you would get 6 plus 6 minus 2. That's 10. Is that right? I don't know. My notes say 12, so let's see. That would be 8. Yeah, it is 12. Okay. Okay, well, in any case, it's a positive number, and p of 1 is a negative number. So I don't actually know what this function looks like, but I'm going to go ahead and draw a picture. So I know that at 1, it's going to be, extend this, 1 and 2. I know that at 1 it's going to be negative 1, so the value of the function there, and this will not be to scale, so say this is 12 up here, so at 2 it's equal to 12, and the function is continuous between them, so I know that it has to pass through the x-axis at some point between 1 and 2. Okay, but so to make that precise, by the intermediate value theorem, which we will abbreviate IVT, by the intermediate value theorem, there exists a C, let's say a point C between between 1 and 2, such that P of C is equal to 0. Okay, now the thing that I want you to get out of this example and just basically this whole thing about the intermediate value theorem is that it is much easier to remember the picture, right, than it is to remember this statement, because I know that things can get, if things get out of order, it will mean a completely different thing, and it's kind of hard to deal with all those pieces. But if you remember the picture and what it means, it'll be much easier to actually use it, right? Okay, so that's all for this section, and don't forget to do the comprehension check question.